Hello, everyone. Time for some discrete math. Let me remind you before we get going here that the test is due April 1st. That's Wednesday, April 1st. And I believe the time I had put on there was 5 p.m. So please do upload your exam by that time. And be on the lookout. I will post something tomorrow in relationship to the first two chapters in Olowski-Dean. Just some problems from those chapters for you to be working through, and those will be the material from which I draw the next homework quiz. Okay, so just be on the lookout for that. Okay, so we started talking about continuous distributions last time, and I said that we will talk primarily about three specific continuous distributions. Now remember, we developed some terminology like density. The density is the function that we integrate to find various probabilities. We also had the cumulative distribution function, which we have here. And we were dealing specifically last time with the example of the uniform distribution, which just means that the random variable could literally be anywhere in an interval of values between A and B, and it's equally likely to fall anywhere within that interval. But again, the probability of being equal to any point is zero, but the probability of being in any small interval throughout the interval from A to B is the same, okay? So, you know, if I just shift that thing around, the probability of falling in there does not change, okay? So I just wanted to remind you that we finished last time. So this was our notation for X being distributed as the uniform. What was the CDF that we came up with? Well, the PDF, let me just write what the density was, right? It was f of x equal to little f of x equal to what? Well, it was 1 over b minus a if a is equal to or less than x is equal to or less than b, and it was 0 otherwise. Okay, so that gave us a graph. I'm just going to kind of draw the graph over here, it's just very, very basic. That gave us a graph that looked basically like this. So here's A, here's B, okay? And the graph was basically at the same height, 1 over B minus A everywhere, okay? So this was at the height 1 over B minus A. Between A and B, and then it was equal to 0 everywhere outside of there, right? So I'll kind of put a couple little open circles right there. And so that's what the graph of the density looked like, okay? So that's the graph of the density, little f of x. Now, what about the cumulative distribution function? Okay, so for that, let me get a different color besides black here. For that, what we did is we like selected an x value that happened to be in here somewhere, and we noticed that the probability that would accumulate up to that, there would be nothing before A, but I would accumulate this probability right here, okay? And incidentally, if x was beyond b, I would have accumulated all of the probability, and I would end up with 1 for x beyond b. So that gave us the following cumulative distribution function. Okay, so it was capital F of x equals 0 for x less than a, okay? It was x minus a over b minus a for a equal to or less than x equal to or less than b, and it was 1 for x beyond a. And of course, the graph of this thing looked slightly different from the graph of the PDF, okay? So I don't know, here's A, here's B, and we said, well, this thing's going to be coming along like this, okay? If I plug in A, I get 0 whether I'm below A or at A. If I plug in x equal to A into the x minus A thing, I'm still going to get 0, right? And we talked about that the graph of that middle function there in this piecewise defined definition is a line with slope 1 over b minus a, okay? And how high up did this thing get? Well, it went up to 1, right? And it's a line, right? So it goes like this. And then what's the deal after this? Well, it's just equal to 1 from that point on. Okay, so it's equal to 0 before A, and then it's equal to 1 after B. Okay, so that's what the graph of the CDF of this thing is. And we also computed things like the mean, also known as the expected value of X. And not surprisingly, we discovered that this was just the average, right? Like you just take the middle point between A and B. And we actually found out what the standard deviation was as well. That was the square root of B minus A squared divided by 12. Okay. So that's just kind of a brief refresher of what was going on with the uniform distribution, if you will. Okay, so that was everything that we discovered last time. All right, so let's move on and let's do a little example here. Assume that the age of kindergartners at Cedar Cliff is evenly distributed over 4.75 to 6. So it could, it's equally likely to fall anywhere within that range. Okay. Again, if we had a density that was kind of spiked up at certain points, that would tend to make the values of the random variable congregate in that range more frequently. Okay. Whereas the uniform distribution is just a nice even distribution everywhere. Okay. We randomly choose one of the students. Okay. Let's define a random variable, find X's distribution. Let's graph the PDF of this thing, the density of this thing, and let's find the PDF. Well, this should be fairly easy. So how do I define the random variable X in this particular case? Well, it's equal to, it's just going to be the age of a random child. Okay. And so what's X distributed as? Well, X, according to what is set up here, X is distributed as uniform on this interval, 4.75, all the way up to 6. And what's the PDF of this thing? Well, that's easy enough. That's just going to look like this. Okay, so here's, I don't know, this is not going to be to scale, but 4.75 up to 6, just so I can see things. Okay. Okay, what do we have? So it's going to be, oops. Let's see. It's going to be what? 1 over the difference of those two things. So 1 over the difference is 1 over 1.25. Okay. And this is what the PDF is going to look like. And of course, before that, it was straight up equal to 0. Okay, so that's what the PDF is going to look like. What is the PDF? Well, we can see it right there. Okay. It's equal to 1 over, right, 6 minus 4.75 is 1.25. That's where that number came from. And that is for 4.75 equal to or less than X equal to or less than 6. And it's 0 otherwise. Okay, that is what's going on with that. Okay. For X between 4.75 and 6, it's equal to 1 over 1.25, and it's equal to 0 otherwise. Okay. All right. So what else is going on with this? Well, let's see. Find the expected value of X. That's easy. Okay. So what is the expected value? Well, mu is equal to, right, so mu, that's another notation for the expected value of X. Of course, that's just going to be 6 plus 4.75 divided by 2. That's what we discovered the formula for the mean actually is. Find the probability that the student is between 5 and 5.5. Find the probability that the student is between 5 and 5.5. Well, 5 and 5.5 fall within the range, or is an interval that lies completely inside of the 4.75 to 6 range. Okay, so that probability, the probability, let's see here, the probability that 5 is less than x is less than 5.5. And by the way, do I really care about equals? The answer is no, I don't. Okay. So what is that going to be? Well, if you think about it, I could take the CDF and evaluate that at 5.5. That would be all the probability up to 5.5. But then I would need to subtract off the CDF evaluated at 5. Okay. And what would that be equal to? Well, again, remember, we're between 4.75 and 6. So I would use that second definition in that piecewise defined thing. So what would happen there is it would be x minus a over b minus a. Okay. A here is 4.75. So it would be 5.5 minus 4.75. That's x minus a over 1.25, okay, minus what? Minus 5 minus 4.75 over 1.25, okay? So this minus applies to this whole thing right here. Notice, right, in this, right, I have this difference. Notice the 4.75s are going to cancel, okay? And I'm going to get 5.5. So look at what this ends up being. It's going to be 5.5 minus 5, which is 0.5, which is the width of the whole interval over the width of the entire interval. And that makes sense, my friends, doesn't it? So the probability of being between 5 and 5.5 years old is just the width of that age interval from 5 to 5.5 divided by the width of the entire interval. All right, so that really does make sense when you think about that. Okay, all right, moving on. Okay, find the probability that he or she is over 5.8 years old in 2 ways. Okay, so I want the probability that x is greater than 5.8. Okay. Well, in 2 ways. Okay. Well, one way is to just kind of think about it. You could just say, well, all right. So what is the width of age possibilities if I'm beyond 5.8? Well, wouldn't that just be like 6 minus 5.8? Okay. So that's like the width of the entire age possibilities over, right? So I have that width of age possibilities over the width of the whole interval, right? Which is 6 minus 4.75 or 1.25. So this would be like 0.2 divided by 1.25. Okay, that'd be one way to do it. The other way to do it, right? So this is way number 1. Okay, what's another way to do it? Well, it would just be to say the probability that x is beyond 5.8 is equal to 1 minus the probability that x is less than 5.8, right? Which is 1 minus f of 5.8. Right, so that's the CDF. I'm using the CDF here, okay? So what would that be? Well, so it would be 1 minus, okay, this value of x, 5.8, is between 4.75 and 6. So I'd use the x minus a over b minus a version of this. So x minus a, so let's see here, so it'd be 5.8 minus 4.75. I'm kind of running out of room here. Minus 4.75 divided by 1.25. Okay, and let's see here. What would I end up getting? Well, 5.8 minus, okay, 5.8 minus 4.75. 5.8 minus 4.75. Okay, so what's that going to be? 5.8 minus 4.75. Oops, I'm for some reason it's forcing me to keep using the eraser, and that is not what I want to do. Hang on a second. Here we go. Yes. Okay, so 5.8 minus 4.75. So what is this? Let me just say that 5.8 minus 4.75. What is that? That's 1. So 5.8 minus 4.75. That is 1 point. That's 1.05. Isn't that right? Okay. So then if I find a common denominator between 1 and 1.05 or 1.25, seems to me it would be 1.25 minus 1.05 over 1.25. Yes. Okay, all I did was find a common denominator. And what's 1.25 minus 1.05? That's 0.2 over 1.25 over 1.25. Okay. Oops. Sorry. Sorry, this thing is not letting me put a decimal point right there. There we go. Okay. Which is exactly what we got before, right? Check mark, check mark. Find the 75th percentile for the age of the students. Find the 75th percentile for the age of the students. Okay, well, what do I mean by the 75th percentile? Well, that means it's a number such that 75% are below it. Okay, so like you've probably taken things like the SAT before, and you've heard things like, oh, you're at the 60th percentile or the 90th percentile, which means that 90% of the individuals are below you, right? 90% of the data is basically to the left of you, okay? So if I want the 75th percentile, what we want here, so let me say it just means I want an X such that what? Capital F of X is equal to, okay, so think about it. I want 75% to be below this. So that would mean that this would need to be equal to 0.75. Okay, so X would be at the 75th percentile if that happened. Well, what is this going to be equal to? So first of all, for it to be equal to 0.75, that means it would have to come from that middle definition again. Remember, to the left of A, it's 0. To the right of B, it's 1. To be equal to 0.75, it would have to be the form, X minus A. X minus A, well, what's A in this case? Well, that's 4.75 over B minus A, which is 1.25. Okay, so I kind of solve for X, okay, and I get that X, the 75th percentile, is going to be equal to 1.25 times 0.75 plus 4.75. Okay, so 4.75 plus 1.25, that's the denominator from the other side, times 0.75. Okay, so what would we end up getting? So X, this X right here is the 75th percentile. Okay, this thing is the 75th percentile. Okay, so what is this X? Well, let's calculate it. And just so that we have it in our hands. So it's 4.75 plus 1.25 times 0.75. I get 5.6875. Okay, so the age would have to be 5.6875. So that means that a child that was 5.6875 years old in Cedar Cliff schools would have 75% of the children below them, okay? Below them in age. That's what that means, okay? All right, so let's clear that out. Okay, and now we're gonna start doing some, we're gonna remind ourselves ways in which we can find probabilities. We've already seen that, you know, we can do integrals. We kind of used integrals to come up with the cumulative distribution functions. We even used geometry. There we actually looked at, you know, rectangles and used geometry to our advantage. Eventually we'll see probability tables, although that's kind of becoming an obsolete tool because Excel is so powerful now and it's so readily available to everyone. Okay, and of course integration are ways that we can find these probabilities, okay? You know, integration has become the tool in the case of continuous random variables, whereas in the case of discrete ones, we were adding probabilities together, yeah? We had sums. All right, so exponential distribution, okay? We talked about the continuous distribution. Now we're going to talk about the exponential distribution. Okay, so the graph of an exponential random variable looks like this, okay? Okay, it kind of hits the y-axis like this, and then it just kind of goes down like this. It decays, okay? It decays from the starting point. And it turns out this point right here, where the decay starts, that's called lambda, okay? And this lambda ought to remind you of something, okay? It ought to remind you of the Poisson. Okay, it ought to remind you of the Poisson distribution, which we talked about before. Okay, this lambda is the same as the lambda from a Poisson process. Okay, and this is the density value. Okay, right, and so if you look at this, it says smaller values occur more often. You could tell that because the density is higher up to the left, and it continues to get smaller and smaller and smaller as you go off to the right here. Okay, so the smaller values occur most often. And of course, the integral from minus infinity to infinity of f of x dx, right? 1 has to be equal to that because remember this thing is giving us probabilities. But of course, this thing is 0 everywhere back here, okay? So we're only dealing with a random variable that happens to only take on non-negative values here. So really the density kills everything for x's below 0. So this thing is the integral from 0 to infinity f of x dx. Okay, so the shape of this thing looks this way. But what is this mysterious density? Okay, so what is the formula for it? Okay, and so that's what we're going to see next here. Oh, wait, so here are some examples of exponential distributions. And I'm telling you, exponential distribution is connected to a Poisson process, okay? Do you remember in the discrete case, we were doing a bunch of Bernoulli experiments and we were waiting for the first success. And we tracked the number of experiments we had to perform. Well, a similar thing, and that was called the geometric distribution. A similar thing is happening with the exponential, but we have a Poisson process where we're observing, you know, over like an interval of time, and we expect to see lambda observations in that period of time. Well, okay, how long am I going to have to wait for the first observation? That's going to have the exponential distribution with parameter lambda, okay? It's the length of time you have to wait for the first observation in a Poisson process with parameter lambda. Okay, that will have the exponential distribution. Okay, doesn't that sound exactly like the geometric, the thing that we had in the discrete case? Right, so the exponential is to the Poisson process what the geometric was to the Bernoulli trials, okay? So amount of money shoppers spend at Meyer often applies for the length of time until some event occurs, which is why this is an important one, because a lot of times in computer science applications, you want to know how long until something happens, some kind of system failure or something like that. Okay, earthquakes, end of a phone call, car battery dying, length of life of any kind of object, okay, even a person itself. All of these follow an exponential distribution, okay? So, and here's the formula. Okay, and this lambda that's sitting here, okay, so this lambda right here, I'm gonna get a red coloration here, okay. This lambda right here is the same as the Poisson, lambda. Uh-oh, I can't see that very well, so I'm gonna switch the color up to black again, okay. This is the same as the Poisson. Poisson lambda. Okay? It's the same as the Poisson lambda. Okay? Very important. Okay, the mean of the exponential distribution is going to be 1 over lambda. Why does that make sense? Think about it for a second. So suppose you were observing, okay, so suppose that you were observing, I don't know, you had y, which was distributed as Poisson with parameter lambda equal to 2, okay, over some interval of time. So an x is going to be equal to the length of time to the first observation. Okay, well then x would be distributed as exponential with parameter lambda equal to 2. Okay, and suppose we were kind of observing this process for an hour. Well, then what is the expected length of time until the first observation? Well, half an hour, 1 over 2. Okay, so mu, which is the expected length of time until the first observation, is 1 over lambda, which is equal to 1/2. Okay, if our unit or if our time interval unit was like an hour, so this would mean a half hour. That makes perfect sense, right? Because we expected to see 2 over the course of an hour, so every half hour we expect to see an observation. Okay. The PDF is given by this thing here. Okay, so here's the PDF sitting right here. Okay, and you see that thing's it's only for x equal to or greater than 0, and it's 0 before that. Okay, why in the world does that thing integrate to 1? Okay, well let's take a look at that. Okay, I'll write that down here because this will help you remember some things from calculus. Okay, if I integrate from 0 to infinity, lambda e to the minus lambda x dx, what is that? Okay, well the antiderivative of this thing, lambda is just a constant. The antiderivative of this thing is just minus e to the minus lambda x. And this is evaluated between 0 and infinity. Okay, and by the way, it's worth noting here that lambda is greater than 0. Okay, so I just want to point that out. Okay, so if I let x go to infinity, of course, e to the minus infinity is 0. And it's going to be minus negative, that thing evaluated at 0, and indeed you get 1. Okay? In a similar way, it's pretty easy to show, right? So that thing does integrate to 1, as it should. Okay, so check mark. In a similar way, to find the CDF, you would have to integrate up to the variable x. Okay, so let me actually let me do that. Okay, so what is the integral from 0 to x? And since I put x in the right, so this is f of x, the CDF. integral from 0 to x. Now I better not use x as a integration variable here because x is now in the limit of integration. So I'm going to do lambda e to the minus lambda t dt. Okay, I need a new variable. And of course, this is just going to be minus e to the minus lambda t evaluated between 0 and x. Okay, so that is the probability of being equal to or less than x. If I plug in x for t, I get negative e to the minus lambda x, minus negative, which is plus 1. So indeed, you get 1 minus e to the minus lambda x, okay, which is exactly what's claimed over here. That is exactly what's claimed over here for the CDF, okay? So that's interesting. Okay, so the mean is 1 over lambda. Again, that lambda is the same as in the Poisson process. We've verified that that thing is indeed a PDF. We found the CDF by integrating. What more could we ask for? Okay, so it's pretty thorough treatment of this thing. Okay? All right, let's see what's next here. How do we find probabilities? Well, again, we can either integrate the density or we could use the CDF. Okay, so a couple of ways that we could find probabilities. You could also use Excel. Okay, Excel has a built-in function for the exponential distribution. Okay, okay, so right, the known CDF, well, I already kind of mentioned that. You could either integrate the density or you can use the CDF that you know that you have, so you don't have to keep doing a bunch of integrals. Okay, but also Excel is a way that we could pull this off as well. Okay, so here's a little example. X is the length of randomly chosen phone call in minutes. Okay, X is going to be exponential with parameter 1/5. So this means that lambda, right? So here, let me change my color here. This means that lambda is equal to 1/5. So what's the mean? The mean is 1 over lambda, which is 5 minutes. Okay, these are minutes, right? So the average length is a 5-minute phone call, apparently, according to this thing. Okay. Draw f of x. Now remember, or draw the density. Remember what I told you? Okay, what you basically have is lambda, which is a 1/5, right here. And this thing decays, right? So this is lambda. This thing decays down like this. That's why, one reason why it's called the exponential distribution. You have exponential decay. We already found mu. Mu is equal to 1 over lambda, which is 5. Okay. All right. So there's that. Let's see. I think we're going to do a couple of other things with this. Okay. Find the probability that x is between 1 and 3. Okay. Now remember, if x is distributed as exponential with parameter lambda, then capital F of little x, right, the CDF is going to be 1 minus e to the minus lambda little x. Okay, and what is lambda in this case? Well, it was 1/5. Okay, so in this particular case, the CDF is capital F of x equal to 1 minus e to the minus 1/5 x. I'll write that as x over 5. Okay. So what's this probability going to be? Well, f of 3, that's the probability up to 3, but then I have to subtract off the probability below 1. Okay. So that's going to be 1 minus e to the minus 3/5. Okay. That's what I get by plugging in x equal to 3 into the CDF, minus 1 minus e to the minus 1/5. Okay, which is equal to, right, the ones actually cancel, surprisingly. Okay, and you get negative e to the minus 1/5, which is e to the minus 1/5. So this is e to the minus 1/5 minus e to the minus 3/5. Okay, that is the exact probability that x is between 1 and 3, that x is between 1 and 3. Okay, what about this probability? Okay, well, okay, so what are we going to have here? Well, it's going to be 1 minus e to the minus 4/5, right? That's just exactly a computation using this thing, yeah? So, okay. So I think I can commit some of these things to memory here, and I want to show you how to use this stuff in Excel. Okay, so be back in just a second here. Okay, I'm over here in Excel. I've kind of copied down the stuff that we knew. We were dealing with an exponential random variable with parameter 1/5. We had the CDF being 1 minus e to the negative x over 5. We computed this probability. These were the exact probabilities using the CDF. Okay, so let me just actually write down a number here. Okay. So actually, I'm going to put a little equal sign right here so you can kind of have that there. So I'm gonna actually put the real number in here. So exp is e. Okay, and I'm going to raise this to the negative 1/5, and then I'm going to go minus exp. Okay, this is e raised to these things, exp to the negative 3/5, and e to the negative 3/5, and I get 0.269919. Okay, so what about this guy right here? Okay, so this is equal to 1 minus exp. Okay, this is e raised to the negative 4/5. Okay, and I get 0.55 whatever. Okay, now watch, I could actually compute this in another way. Watch. Okay, so it's a probability of 1 less than x less than 3. Okay, equals what? Well, watch, I go equals x. Now I'm going to use the actual distribution. See this thing that says distribution right here? Okay, I can click on that. What's my x here? Well, first of all, I want to go all the way up to 3. Okay. What's my lambda? Well, it's a 5th. Cumulative? Yes, true. Okay. But then I want to subtract off exponential distribution. I want to subtract off the stuff up to 1, right? So lambda is still a 5th. And yes, I want it to be cumulative. And there it is. It's exactly the same as what I got computing this thing by hand, basically. Okay. So probability that x is less than 4 equals what? Well, let's do this. So this is going to be 1 minus, or no. Right, I can just straight up use the cumulative distribution function. So it's going to be exponential distribution. What's my x? 4. Lambda is a 5th. Cumulative, yes. And there it is. Same exact thing I got doing it in the other way. Okay? All right. All right, one more thing, and I think we're going to be done. We want to find what I want to do here is find the 90th percentile, of this particular distribution. So again, what was the situation we found ourselves in? X was distributed as exponential with parameter lambda equal to 1/5. Okay. So the CDF is equal to 1 minus e to the minus x over 5. Okay. And we want the 90th percentile, okay? So that means we want an x value, so we want x, and this is going to be, again, greater than or equal to 0, obviously, because I don't start even accumulating probability until I get beyond 0. I want x greater than or equal to 0 such that what? F of x, the CDF, I've accumulated 90%. 90%. So what does that mean? Well, that means that 1 minus e to the minus x over 5 is equal to 0.90, okay? Which means if I were to kind of, shift some stuff around, like move this over and move the 0.90 over, that would mean that 0.10, because 1 minus 0.9 is 0.10, is equal to e to the minus x over 5. Take the logarithm of both sides, natural logarithm. You get that the natural logarithm of 0.10 is equal to, natural logarithm of e to anything is just the power. So that's going to be negative x over 5. And then just multiply through by negative 5. So x is equal to negative 5 times the logarithm of 0.10, whatever that is. Okay, and I can actually compute that on my calculator. Okay, so negative 5 times the natural logarithm of 0.1. Okay, I get 11.513. 11.513. 11.513. And by the way, this is in minutes. Okay, remember we were talking about phone call lengths. The average, right, the mean for this problem was 1 over lambda, which was 5 minutes. Yeah, so it's not surprising that to get to the 90th percentile, I would need to have a phone call that was over 11.5 minutes long, so that 90% of phone calls would be below that. Okay, so this guy right here, this is the 90th percentile. 90th percentile. Okay, the 90th percentile. What's another way that I could see that, or that I could get all this stuff? Well, I could go and actually use Excel. So I'm going to show you that, and that will be the very last thing that we do. I'm not actually going to do the last example in here. I think that this is more than enough what we've done so far. So I'm going to show you how to do that in Excel here, and we will be done. Okay, here we are over here in Excel again. Just wanted to show you, one more trick that you can do over here. Now, in this case, there are some distributions, like when you type them in, like the exponential, for instance, where it will give you the option of actually finding, like if you input a percentage, it will tell you the x value that gives that. It'll give you the x value that gives that. For instance, the normal distribution does that. So this one right here says normal inverse distribution. See that? This says returns the inverse normal cumulative distribution for the specified. So it says inverse. That means that you're going to input a percentage. So like if I put in here, it says, give me a probability that you want below this thing. Give me a mean, a standard deviation, etc. And it will actually tell you, here's the x value that corresponds to that. For the exponential distribution, that doesn't actually happen. There isn't an inverse option. Inverse means you plug in the probability, they tell you the x from the CDF, as opposed to you giving the x and they give you the probability. Okay, for the exponential, there isn't an inverse because it's so easy to solve for the x itself. Okay, and we already did that. It was 11.513. But I just wanted to show you. Something. Okay, so this thing was negative. Okay, let me just say this was equal to negative 5 times the natural logarithm. So log. Let's see. Returns the logarithm of the number to the base you specify. Right. So log number. I wanted the logarithm of 0.1, and what's the base? Well, the base for this thing was what in the world? Was exponential of 1, right? It's the number e. I don't think it would have worked for me to just put e in here, right? And I get 11.51293. Okay, that's exactly what we got when we just solved with our by hand and used a calculator. But one thing I want to point out is, watch this. So the probability that X is below this number, 11.51293, okay, what should that be equal to? Well, it should be equal to 90%, and it is, watch. If I go exponential distribution, and I plug in this X value, what was our lambda? Lambda was 1/5, cumulative, yes. And you should get 90%. Let's make sure. We do, okay? So the amount of data, the percentage of data below that is 90%, right? So that's why that number is at the 90th percentile. Okay, I think that's all I wanted to say for now. Okay, we're completely done with chapter 5. Remember, we studied the uniform distribution. We studied the exponential distribution. Don't forget that the exponential distribution is explicitly connected to the Poisson. It's the waiting time to the first observation that occurs, okay? So those two bits, or those two continuous distributions, are pretty important, okay? And we're going to study one more continuous distribution that's going to be exceedingly important for us, namely the normal, okay? And that's all I have for now.